Welcome back. We will continue with the revision of key theorems and then solve some problems. So we have seen Lyapunov stability and asymptotic stability to this function theorem, and one of the key results, and then it's this particular result is important for more than one reason. Though I don't present everything here, this is a summary. One can actually show asymptotic stability even if you have v dot less than or equal to 0, right? Let me go through the result first and then remind you some of the other things that we haven't considered. So, we'll have the same setup, x dot equals f and things like that, and slightly different in terms of assumptions. We have to have a positively invariant set, a compact set, and things like that, on which we will define this Lyapunov function candidate. And this Lyapunov function candidate will satisfy v dot less than or equal to 0, and therefore we cannot conclude asymptotic stability from the original Lyapunov function theorem, right? But the nice thing is basically if you have a bounded solution, bounded trajectory, then theory, ODE theory, the flow theory or solution theory guarantees that it will reach something called a limit set, right? And that limit set is going to be non-empty to start with, and then it's going to be bounded, compact, closed and bounded, and then finally it's going to be invariant, right? So we use that powerful result to essentially explore convergence behavior of many of the systems without necessarily bothering about stability as such, right? And you can actually use any function v that's not necessarily positive definite and things like that, and as long as v dot is less than or equal to 0, we can actually use that fundamental theorem that came from invariant set theorems of LaSalle can be used to show convergence to some asymptotic behavior, right? With respect to specifically asymptotic stability, suppose if v happens to be positive definite and things like that, and v dot is equal to less than 0, so then we actually know that v is going to go to 0, right? Sorry, v dot is going to go to 0 in at least in particular these particular time invariant cases. And when that happens, we basically let this set R, and then we look into this set R, look for invariant sets, because we know that we are going to go to invariant sets, right? So look for all invariant sets, and we can guarantee therefore our solutions reach to one of the invariant sets, right? So perhaps therefore we can conclude that the biggest invariant set is where it's going to go, right? That's the general result. But if the only invariant set within this set is the origin, then basically we conclude convergence to 0, and then by the fact that this is a basic Lyapunov function, we have Lyapunov stability. Combining both of them, we can conclude asymptotic stability, right? And this is a very useful result in many scenarios, and that's why it's of independent interest, not just for asymptotic stability, right? So let's actually solve one small problem and move on from there, right? So basically I have this particular system, and then basically a Lyapunov function candidate, which is positive definite and all this nice, and then basically let's see, I'm going to compute v prime f, which is going to be x1 cube x2 times this x2 minus x1 x2 square minus x1 square x2 minus x1 cube plus x1 power 4 x2, right? And therefore v prime f is going to be simply x1 cube x2 minus x1 power 4 x2 square minus x1 square x2 square minus x1 cube x2 square, sorry, no square, just x2 plus x1 power 4 x2 square, right? So this cancels with this, and this cancels with this, essentially giving us minus x1 square x2 square, right? So this tells us the R set that we are talking about is basically going to be x1 x2 x1 x2 is equal to 0, right? So it's basically we have to look for invariant sets within the set where x1 x2 is equal to 0, right? So if you start in that invariant set, x1 x2 is going to be remaining 0, Okay. So let's go back to the original system. If you actually look at this, so this x1, x2 part is going to be 0, x1, x2 is part going to be 0, and then we will end up with something. But I'm going to basically do this magic, basically take this first equation and multiply with x1 on both sides. So I'm going to get x1 x2 dot is equal to x1 x2 minus x1 2 square, x1 square, x2 square, but these are 0, right? So on that invariant set, what we are going to satisfy is x1 times x1 dot is equal to 0. But we know that x1 dot is derivative of 2 times x1 square. So therefore, x1 square has to be 0. So therefore, x1 has to be 0, right? So we conclude that x1 is going to be 0, right? But no way of guaranteeing x2 is equal to 0 at this particular time. And therefore, we take the second equation, again multiply with x2, right? And I'm going to get yeah, so we already know that on this particular invariant set x1 is 0, so this I'm not going to bother. So this is also, yeah, so we're using very similar logic as the first equation by eliminating x1. Now that we know x1 is 0, we will conclude that x2 dot is also going to be 0, so therefore x2 is going to be 0. So this is therefore, though v dot is minus x1 square, x2 square, basically we can say only one of them is 0. By concluding for sure x1 is 0 and then substituting that in the second equation, x2 is also going to be guaranteed to go to 0. So that tells us 0 is the only invariant set that this system can reach, right? So this is a Lyapunov stable equilibrium point. Why? Because v is a good Lyapunov function candidate, it's positive definite, and v dot is less than or equal to 0, and the only convergent point is 0. Therefore, this is indeed globally asymptotically stable. Okay. How do I know global convergence? Because you know, v is radial and bounded, so the conclusion can be automatically extended to the entire space. Okay. So hopefully you appreciate the logic of basically how to use this Lyapunov function theorem, right? Though I say this is end of lecture 11.4,